All right, today we're going to be talking about section 2.2, contextualizing linear functions. Let's go to work. Contextualizing linear functions. First, what does context mean? We've talked about this in section 1.1. Real life situation. This is where the rubber meets the road. Real life situation. Okay? I talk a lot about math being more than just numbers now, right? It's about reasoning and logic. I want to figure out how to use this math stuff that you're learning in these classes and apply it to a real life situation. Putting it in context. Reminder of what is a function. What is a function? Dalen? Very good. Every input has exactly one output. We've spent a lot of time on that in the first unit. We remember what a function are. So we've talked about contextualize. We've talked about functions. We've spent a lot of time on those. I'm not going into those any further. How about linear? What does it mean to be linear? Ms. Stahl? Okay. I'm going to erase the first that you said there, and I'm just going to stick with the second part. Has the first degree. Okay. It is to the first degree. Its graph is a straight line. One more thing about linear is it has a constant rate of change. Has a constant rate of change. Now, as we talk about linear, I'm going to talk about a couple different things here. I'm going to give you one here that's kind of foreshadowing in the future. Okay. I think it's the next unit. No, 2 units from now, when we start talking about polynomials. Okay. You're going to hear me say the word standard form. When I talk about standard form of polynomials, that means we want to get our terms lined up from high to low. What I mean by that, terms lined up high to low, is if I had 5x to the fourth minus 3x cubed plus 7x squared plus x minus 5. What I mean by terms lined up high to low is my exponents will be high to low. It's not wrong if you don't put your exponents in some other order, but we like to be organized in math. Yeah? So we want to get our terms lined up from high to low by the exponents. So you'll hear me say, and let's make sure we put that in standard form when we get to that point. And what that means is just put the exponents from the highest to the lowest. Now, I changed colors there because it's not really something I'm dealing with now. Just kind of introducing it for you. We'll come back to that later. But linear functions also have standard form. And the standard form for a linear function is ax plus by equals c. Basically, what I want you to get out of that is that your x and your y are on the same side. I hope that you realize as you look at that, we've already dealt with some of those. Matter of fact, we did 2 of them today when it was given to us something like 2x plus y equaled 7. And the first thing we did was get the y alone, right? So you've seen them. in standard form already. I just want you to know that when the x and the y are on the same side with a linear function, we call that standard form. We'll be diving more into standard form at a later time. The next form is slope-intercept form, and I know that you know that one already, so who can give it to me? Go ahead, Dalen. Y equals mx plus b. And that's what this whole section is about, is diving into slope-intercept form and realizing everything that each part of the slope-intercept form represents. In your reading, this unit started talking about two new words, and that's independent and dependent variables. The independent variable is the one that stands alone. We already know that the independent variable is the, which one? The x. Oh, I like it, Miss Stahl. You guys missed that. She's like, yeah, I like it. Yeah, it's the x. It's the x. And then the dependent variable is the y. But the dependent variable always is determined by the x. Okay? Is determined by the x. Wants a job. Wants a job. Chikai, you want a job? Okay, I'm gonna give you a job. I'm gonna pay you $10 an hour. Okay? How much are you gonna make on that job? So it depends, doesn't it? How much you make would depend on how many hours you work. Yes? So if you worked 5 hours, how much would you make? Okay. In that situation, which is the independent variable? And which one is the dependent variable? What do you think, Cody?
I didn't hear.
She said the independent was the 50 and the dependent was the 10. Ava?
Independent is $10.
Exactly. You had to wait to tell me how much money she made until we knew how many hours. So that hours would become or would be the independent variable. And that's what we're going to want you to grasp is in the situation, determining which thing that you're going to be talking about can stand alone, which is the one that we need to know before we can find out the other one. And that's what independent and dependent is about. Independent can stand alone. The dependent variable is determined then by the independent. Now, we use X and Y, but especially in this section or in any section for any matter, you could use any variable you want. They could have a G and an H, an M and an N, an A and a B. You don't have to use X and Y. One thing I want you to remember is on the graph, if we use G and H, my axes get renamed to where the x-axis would now be the g-axis and the y-axis would then become the h-axis. Or, watch this, the h-axis is wonderful, but could it also be called the g of x axis? Yes, that's function notation, remember? How about this? How about if I give you one that has an independent variable of c and a dependent variable of d? What would my horizontal axis be? And my vertical axis? D or C of X. Yes, we're rocking. We're rocking. Okay. Slope. What is slope? Come on. What is slope? It's the rate of change. Anybody else? rise over run. Another one. Delta y over delta x. One more. How about this? Can I put this there? Y2 minus y1 over x2 minus x1. Can I put that there too? Yeah, that all goes there. The y-intercept. So y-intercept. Initial value. Or the constant. Yes? All right. So one more time. Here is our slope intercept form. It's our favorite form. The y-axis, y variable can be called the dependent variable. It can be called the output. I want you to copy this down. Make sure you get this copied down. M is the slope or the rate of change. X is the independent variable or the input. B is the y-intercept or the initial value. And today we're adding y is also known as the range. We've talked about that. Slope is also rise over run. X value is the independent variable, the input, or the domain. And the B is the y-intercept, the initial value, or the constant. Give you a minute to make sure you have that written just as that. And let's go into a couple problems to see if we can identify each of them. It's important that you know all these different names because that's how you identify what you're talking about. It's always been amazing to me for years and years and years. You ask us a question, and everybody looks at you like, I have no idea what you're talking about. And then you reword it, and all of a sudden, you get it. Literally, in contextualizing, the hardest thing is identifying what you're dealing with. You can identify everything that you're dealing with. You already have shown multiple times that you're good with y equals mx plus b. We're great at graphing it. We understand all the parts of it. We know that the initial value is at the end, and that's where we start. And the rate of change allows us to graph it. So there's a lot of stuff that we know about this y equals mx plus b. Matter of fact, that was the first equation you gave me this year. So everybody got that? All right, let's look at number one. I'm only going to do two of them for you today. We're only going to do two together. And basically what I'm looking for is we need to be able to identify the rate of change, the initial value, the independent variable, the dependent variable. Then describe what that rate of change and initial value mean in the context of each situation. And then finally, we're going to write the equation in linear function. Well, come on. If I give you the slope and the y-intercept, can't you give me the equation in line like super easy? Of course you can. So, question number one. A 2.5-foot rocket's distance traveled in meters based on the time in seconds t is modeled by the following equation. I don't want you to see the equation, so I'm going to hide it for a second. Okay? So we got two variables here, d and t. Which is which, and how do you know? Yes, dear. Okay, so she's saying that our T is our X and our D is our Y. What do you think, Devin? What do you think? You agree? Okay. So D is based on T. T is independent, or Y is based on or dependent. Can you find that context clue of based on to know which is which? So what's my dependent variable? D. What's my independent variable? T. Okay. Now, everything else is going to be based on this function. All right, there's the function given to us in equation form. Wow, that looks very familiar, doesn't it? What form is that in? Y equals mx plus b. So what's my rate of change? What's my initial value? What's the equation of the line? Well, it's already given for us, so pretty simple. Cool? Let's look at number 2. Let's look at number 2. Oh no, I don't have a graph here. Okay, the cost of 6 people to travel in a taxi in New York City, C, is based on the number of miles driven. M. It's shown by the following graph. What is my dependent variable? C. How do you know that? C is based on. What is my independent variable then? M. Now, however, will I find my rate of change and initial value? Cody? Yeah, from the graph. Cody, it's probably easier to find my initial value, isn't it? What is my initial value here? 2. It's right there. It's that y-intercept, or it's whatever the function is, or the value of the function when it's 0. So here it is 2. I'll stop there. Your homework is 2 through 18 evens. 2 through 18 evens. Okay? Y'all have a great day. Yes, Cody. Or Mr. Garbrandt. Question?